This video covers gradient descent. I'll talk about the intuition behind gradient descent, followed by the equation to compute it and the algorithm for stochastic gradient descent. Then I'll work through a case example showing a single step of gradient descent. Gradient descent is a method used to find optimal weights for classification models. The goal in finding optimal weights is to minimize the loss function defined for the model. For example, if the model uses cross-entropy loss, we would want to find weights W and a bias B that minimized cross-entropy loss. The way gradient descent finds these optimal parameters is by first figuring out the direction of the function's slope, and then just moving in the opposite direction until it converges at a minimum. This works particularly well with logistic regression because its loss functions are convex. That means that there's only a single minimum, and no matter where you start off the gradient descent algorithm, it's guaranteed to find that minimum sooner or later. We can see that intuitively with the example on the right here. On the x-axis, we have our possible weight values ranging from negative on the left to positive on the right, and on the y-axis, we have our loss values ranging from low at the bottom to high at the top. We plotted our loss function curve in red. At the point in our loss curve where the smiley face is, we see that there's a negative slope. So there's higher loss on the left in the negative direction than on the right in the positive direction. So following our guidelines, that means we'll go ahead and move in the positive direction for our next step. We go ahead and do that, and we see that now with our updated, more positive weight value, our loss is lower. So that intuitively showed how this process works, but there are a lot of little details that we still need to fill in. For example, how much do we move? We can imagine that with the previous example, if we'd moved too far, we would have ended up over on the right with just as high of a loss value. In gradient descent, we move an amount equal to the value of the slope. So that's the derivative of our loss function curve with respect to a given weight, weighted by a learning rate eta. We can fine-tune our learning rate to our specific task, and a higher learning rate means that we move our weight more at each step. So at a given time step, a single weight will be updated according to the equation you see here. Now remember that it's highly unlikely that we would just have a single weight to update in our entire logistic regression model. That would mean that our input was represented using only a single feature. In reality, we typically have an input feature vector. So rather than our gradient being a single slope in that case, our gradient will instead be a vector of the slopes for each dimension. This means that in order to update our set of weight parameters, theta, overall, we would take our original weights, find the individual slopes for each of them, multiply each of those slopes by the learning rate, and then subtract that product, which is a vector, from our original vector of weights. So with logistic regression, we're pairing gradient descent with a cross-entropy loss function. I went ahead and rewrote our cross-entropy loss function here, and then took the derivative down below. So for a given weight wj, we end up needing to find the difference between the actual and predicted values by taking the sigmoid of the weighted combination of inputs and then subtracting the actual values, and then multiplying that by our corresponding input value xj. When we apply gradient descent to real-world problems, we generally recompute the gradient of the loss function after each training instance. And the most common way to do this is by using the stochastic gradient descent algorithm. Here's how it works. We start out by initializing our weights to 0, and then we just start looping through our training instances. For each training instance in random order, we compute the gradient and then update our weights based on the gradient we computed. We do this over and over until we reach convergence, which means we've reached a point where our weights don't change anymore, or they change only a very tiny amount that we deem acceptable. Then we return those optimal weights. We can work through an example to see how a single step of gradient descent works in practice. So here we again have this same example we've been following for this module. If you're watching these videos out of order, you may want to go back and review the videos covering a basic logistic regression classifier and cross-entropy loss. But basically, we have an instance that we know is stochastic, and we have a feature vector where we've extracted features for the instance. In the previous examples, we've also had weights for those features because we've assumed that our logistic regression model is already trained. But now in this example, we're going to assume that that's not the case. So instead, for now, our weights are just initialized to 0. We'll also initialize our bias to 0, and we'll go ahead and set our learning rate to 0.1. As I mentioned previously, learning rate is something that you can play around with and fine-tune according to your task if you want. As a reminder, I've gone ahead and included the equation for a single step of gradient descent here. So we have 4 weights that need to be updated. We have weights 1 to 3 that correspond to features 1 to 3, and then we have a weight for our bias, which was also initialized to 0. We'll start out by computing the gradient, so we need to find the slope for each one of those weights, given our current training instance. Now, our wx plus b is going to remain the same in each of these cases, and it's actually going to be 0 because our weights and bias term are currently all initialized to 0. So we'll start out by just taking the sigmoid of 0, which ends up being a value of 0.5. We'll go ahead and substitute that into these equations, and we'll also replace the generic y with the value of 1, which is the actual label for this instance. So for weight w1, we'll need to take 0.5 minus 1, so that's negative 0.5 times x1, which is the value of feature number 1. We can see from the table that feature 1 has a value of 1. So negative 0.5 times 1 is negative 0.5. We'll repeat with weight w2. So in that case, we're taking negative 0.5 times x2, which is 0 for a product of 0. For a weight w3, we'll again have negative 0.5 times 1, so we'll have negative 0.5. And then for a bias term, we don't have a corresponding feature that we're multiplying this by, so we just have negative 0.5. So we have our gradient, and now we need to use that gradient to compute our updated weights. Our initial weights were all 0, so we'll replace theta t with the 0 vector, and then we'll subtract eta times our computed gradient. Remember, we decided to set our learning rate to 0.1, so that means we'll multiply each of our computed slopes by 0.1. So that means now we'll be subtracting a vector containing negative 0.05, 0, negative 0.05, and negative 0.05 from our 0 vector. That'll give us our final updated weights of 0.05, 0, 0.05, and 0.05. So we've made it through one step of gradient descent. Now we would just repeat this with our other instances until we reached convergence.